Hello students. So in this class we are going to discuss about more details about escape velocity. Okay. Escape velocity. If you remember, we have discussed in the last class that from the surface of Earth, if there is a particle of mass m is being projected with a velocity escape velocity. This is the Earth's mass, and then it can escape the gravity in outer space. Its velocity becomes 0. Here this distance becomes infinity, right? And it was projected from a distance of r from center of Earth. So we calculated that by energy calculation, energy conservation, escape velocity root under 2 gm by r, or in terms of g2 g into capital R. Now suppose if instead of surface of Earth we can project it from some height, let us say the same case, and we are throwing that body from some height. Okay. Then what will happen? If you throw it from some height, then what will be escape velocity? That means now you need to consider the initial height as r plus h, because this is some height originally present in that body. So same way energy conservation, when you are applying, final condition has to be same, that when it reaches infinite distance x equal to infinity, this velocity becomes 0. So this velocity becomes 0. So finally there is no total energy. So initial energy only is the energy which has to become 0. So initial and final energy has to be equal to 0. Equate that. So same way, minus gmm by r plus h half m v escape square is equal to 0. So escape velocity at this height will be in the same manner. You can calculate root under 2 gm by r plus h. Okay, and this also can be written as root under 2 g into that r plus h you have to multiply. Okay, so you can see that the thing is that capital R can be replaced by r plus h. Okay, that's the only change that will happen in this formula. Okay, also in terms of density, when you are converting, you make sure you have to write mass as density into volume. Mass is density volume. Volume is 4 by 3 pi r cube. So when you are writing this root under 2 g rho into 4 by 3 pi r cube, and this is r plus h, so it will become 8 pi by 3 g rho r cube by r plus h. This is how it will change, right? Okay, now we can consider some cases like when you are throwing a body from surface of Earth. Let us say you are projecting a body from the surface of Earth, and we can take 3 cases. Case 1, case 2, and case 3. So suppose you project a body of mass m, but this velocity is less than escape speed. Second case, which already we know that, so we don't have to derive this case. So it's mass m, you throw with a velocity v, which is equal to escape velocity. And third case, you throw this with a speed greater than escape velocity. So definitely in this case, second case, if you take first case, it will not escape definitely. So some height it will go from the surface of Earth, some height, right? This is r. So that height we can calculate where it is going. That is the maximum height that it will go, right? In this case, it will go to infinity and it will stop. This already we know that. This case, it will go to infinity and it will not stop at infinity. So when this distance becomes infinity, it will be having some velocity. Okay, we task it is. So we want to calculate that. So let us do this first calculation, first case. So when you are projecting it, so right now velocity is less than that. So half mv square you are giving, and potential energy minus gmm by r. It has gone to some height where it is stopping. So kinetic energy 0. Potential energy is minus gmm by r plus h. So from this now we can try to solve what is that h, isn't it? We can try to solve the height h. So after you solve this height, you can bring this side now and try to solve this. Small m anyway will get cancelled and we can solve it. So what do you get from here? Half mv square will become equal to gmm into h by r plus h. Okay, so simplify this case and you will be able to calculate h. Right? H can be calculated. H will come in terms of capital R and escape velocity square by v square minus 1. This we are just writing in terms of escape velocity, right? So the height that can be achieved, if it is not equal to escape velocity, it is less than escape velocity. Okay, so denominator will be greater than 1, you will get will be getting some height, right, after substitution. And if escape velocity is k times, sometimes in question take if the velocity is k times the escape velocity, k is just a factor, so that height can be calculated here as k square minus 1, right? K times it is, we will be able to calculate that. So escape velocity is k times, then you can just multiply this and that side you can calculate. Okay. From center also distance we can calculate. So all of the calculations we can do, right? Then let's go to this case. Second case already we know. A third case you can take what will happen if it is going to that height. That means infinity it will have some speed. So what will be the speed at infinity? So initially kinetic energy half m v square, potential energy minus gmm by r plus r, right? Final kinetic energy half m v dash square, potential energy is 0. So calculate from here v dash, okay, or v at infinity. V at infinity, better you write v at infinity. V at infinity means it is not that velocity has become infinity, it is the velocity at infinity. So velocity at infinity can be calculated this as root under v square minus v escape velocity square. Okay, after you simplify this in terms of escape velocity, you can calculate, right? So these are some of the case studies which can be done here in this. Then some of the things which we should know more about escape velocity is this escape velocity from Earth, or Earth's escape velocity is nearly 11.2 km per second. Okay, and escape velocity from Moon is approximately 2.31 km per second. Okay, so I think these are some of the things. Also we should note that escape velocity does not depend on how you are projecting, does not depend on angle of projection. Sometimes people may think that we can give some angle and we can escape it, but you can project it from surface of earth at any angle, like this, like this, like this, any angle. Okay, it will not depend on the direction, and also it does not depend on the mass of the body, does not depend on angle of projection, and it doesn't depend on mass of the body. People may think that if you have to project a very large object, then maybe we need to give very large speed. No, escape velocity is same. Okay, so I think with this we have covered this topic. Then we can go to orbital speed. Let us discuss orbital speed. Orbital speed of satellite. Satellite or any object, not necessarily satellite. Suppose, for example, this is Earth or any planet, and this is a satellite which is revolving around Earth in a orbit. Right, some circular orbit it is going around. Now, from here, this distance is, let's say, R. This is of course H, and this is capital R. Right. So, as it is going around the Earth, we can see the force acting on the satellite is only due to gravity. Right? Gravitational force is acting. That gravitational force is the centripetal force. Centripetal force. So, gravitational force is Gmn by r square. Centripetal force is mv square by r. So here, after we cancel it, this v what we get is root under Gm by r, isn't it? For small mass can cancel. This can also be written as small g into r. Okay. Here g is not the gravitational acceleration due to gravity at the surface. It is that height. Here g is equal to Gm by r square. It is at that location of the orbit. Okay. This is what is escape velocity. Right. Then there are many other things that we can discuss here, like suppose a particle is rotating near the surface of Earth, then we can also calculate the orbital velocity at the surface or close to the surface of Earth. So orbital velocity close to the surface of Earth, orbital velocity of satellite close to Earth's surface, that will become root Gm by capital R. Right, it is going to be 1 by root 2 times the escape velocity, and when you calculate it, it will come near to 7.92 kilometer per second. Okay, or nearly you can see that this is 8 kilometers per second. That's the escape velocity. Okay, right. Then we may also calculate some, for satellite. If we are discussing, we can discuss some other things, like if you take satellites. So basically satellite of two types. Suppose if you take this Earth, right? So satellite can be projected and it is going in a plane which is equatorial plane, you can say. So this satellite which is going in this way is called geosynchronous satellite. Geosynchronous satellite means whose angular velocity is same as Earth or time period you can say. Time period is same as Earth, 24 hours. Omega also we can calculate 2 pi by time period. You can substitute and calculate. So angular velocity of that satellite is same as that of Earth. That means always it will be at the same point it will look, because it is also rotating the same speed. So a particular satellite kept at a place, it will look like it is stationary there. Okay, and there are other satellites which can be along the polar orbit. So that satellite is called polar satellite along the north-south. Okay? This satellite is called polar satellite. Polar satellites, the time period of polar satellite is not that much. That is quite small, maybe in few hours it will be, right? So polar satellite, their time period is few hours. Few hours. Okay. So how much it will be? It will be around maybe near to 1 hour or 2 hours like that. Generally it is of 100 minutes, nearly 100 minutes. Not even 2 hours, less than 2 hours. Okay. So so many times it will be going around the Earth's surface. So polar satellite will be capturing images on the surface of Earth many times, and it can study different things going around on the surface of Earth. Geosynchronous satellite is monitoring a particular region of the Earth. Okay, right. So these are some of the things. More detail about this in theories you can read from the textbooks. Right. So thank you for attention. Then we'll see you.